Hey everyone, how's it going today? We're gonna solve a real quick problem today. I'm setting up the stream here. 1 second, guys. I hope you guys are doing okay. Alright guys, so I am going to go ahead and just jump in. We're just gonna go ahead and define the problem here. This is the problem, guys. Okay, here's the problem. So we have a runner that is sprinting around a circular track. So I'm going to go ahead and I'm going to draw a circle to represent the circular track. And it has a radius of 100 meters. So we have a 100-meter radius. From the center of the track. The question is, so there's another bit of information here. There's a friend standing away from the center of the track 200 meters. So if this is 100 meters, another 100 meters, and I have my friend right here. So that distance there is going to be, I'm going to draw it in white, 200 meters. And my runner over here. The question is, how fast is the distance between the friend and the runner changing when the distance between them is 200 meters? So how fast is distance changing when distance is 200 meters between friend and runner? Pretty simple, right? Very straightforward setup of a problem. And I think I'm going to solve this 2 different ways. There's 2 different ways that I'm going to solve this. And the very first way that I'm going to do this is I'm going to go ahead and scroll down a little tiny bit. I'm going to redraw a circle. I'm going to represent the position of the friend by a point. And I know that the runner, he lives on the circumference of the circle. So he's going to be somewhere over here. Let's say right here at this point. We can actually draw a triangle using these 3 points. Kind of like this one here. And there's a few things that are going to be constant. For example, the length of the triangle at the bottom right here is going to be a constant 200 meters. The length from the center of the circle to the runner is going to be a constant 100 meters. And we know that the problem that we're trying to solve is going to be the case where the distance between the friend and the runner is 200 meters. And there's an angle theta right here. So let's write an equation that relates the distance right here. I'm going to write it as d for right now, because that's the variable. That's the thing that's changing with time. And that's what we're trying to find, that distance with respect to time. The change in distance with respect to time. So I'm going to write an equation that relates d And well, there's another variable here. There's the angle theta that's changing. So I would say best equation to use here would be the law of cosines, which is going to be d squared is equal to 200 squared plus 100 squared minus 2 times 200 times 100 times the cosine of theta. And I can go ahead and I could go ahead and take a derivative here. So I'm going to take a derivative with respect to time. The reason why I wrote these distances as numbers is because those are constant, so we don't need to worry about any sort of variability with them. So take a time derivative. With respect to time, we're going to get 2d times dd dt is equal to 200. The derivative of 200 is 0 plus 0, because that's a constant, minus 2 times 200 times 100. Derivative of cosine is negative sine of theta, but you gotta remember, theta is changing with time. Theta is definitely changing with time, so we gotta put d theta dt. And I can do a little bit of simplification here. So I'm going to rewrite this as 2d dd dt is equal to negative times negative is positive. So that's going to be 2 times 200 times 100 sine of theta d theta dt. And we got another variable here. Actually, we have two variables. We have the angle theta as a variable, and we have d theta dt as a variable. So a couple things we can do here. So we do want to know what this angle theta is, and I'm going to go ahead and use a different color here to represent the next stage. So what is theta? What is theta? We can use the original equation and solve for theta when d is 200. So solve theta when d equals 200. So we're gonna go ahead and reuse the law of cosines here. 200 squared is equal to, that was 200 squared plus 100 squared minus 2 times 200 times 100 cosine theta. These 200s cancel, so we're going to be left with negative 100. I'm going to subtract 100 on both sides. That is equal to negative 2 times 200 times 100 cosine theta. The negatives cancel. And I'm going to go ahead and divide both sides by 2 times 200 times 100. Just save ourselves a few steps. 2 times 200 times 100. That's going to be equal to, one of the 100s will cancel. So we're going to get 100 over 400, which is equal to 1/4 sine of theta. No, sorry, 1/4, which is equal to cosine of theta. I don't know what I'm thinking. There we go. So I can take the inverse cosine here. Inverse cosine of 1/4. And if your calculator is in radians, that should give us 1.318 radians. Okay. That's equal to theta. So this is our theta. And now that we have theta, we can find the next step, which I'm going to start using a light blue. We want to find out what d theta dt is. we're going to need another equation for this. And we can use the fact that the arc length is equal to r theta. And luckily enough, using this equation, s equals r theta, it matches with the theta that we're using right here. So we're okay with the variables there. What I'm going to want to do is take a time derivative of this. We're going to get ds dt is equal to r d theta dt. And ds dt, the nice thing about this is that because the speed, the velocity, or how can I explain this? The rate of change around the circular track is constant. We know that this is going to be the velocity that the runner is running at. So we can replace ds dt for v, and that's equal to r d theta dt. So we could rewrite d theta dt as v over r, which is great. That gives us constants to work with. So now that I have d theta dt, we can go and look at that formula, or well, the last line that we were left off with over here. And then we could just go ahead and plug in for v over r. So what do we have? We have, I'm going to use a different color, purple. 2d dd dt is equal to 2 times 200 times 100. Sine of theta d theta dt. And I'm going to go ahead and divide both sides by 2d. So we're going to get 2d, we're going to get dd dt is equal to 2 times 100 times 200 sine of theta d theta dt over 2 times dd. We know it's 200, so 2 times 200. A few nice things cancel out. And let's go ahead and plug in what we know about d theta dt. We know that it's the same as v over r. So that's going to be 100 sine of theta times v over r. R is 100. So 100 divided by 100 cancels. So we're going to get v sine of theta. And we know theta. We know that theta is equal to 1.318 rads. So we can go ahead and plug in our numbers. V is 7 meters per second, was that? Yeah, the problem says 7 meters per second times sine of 1.318. So we could go ahead and plug this into our calculator. 1.318 times 7, and that gives us an answer of 6.77, I guess I could say 6.78 meters per second. Now, one thing to note is there's actually two angles where this can work. There is, if we look at the triangle up here again, there's the one that you see here, and then there's this configuration here. And that's the reference angle that you can use. If you were to do that, if you were to use that other angle, you're going to get negative 6.78 meters per second squared. And that makes a lot of sense, because if you're running around this circle at a constant rate, when you're approaching your friend, it's going to be a negative number because that distance is shortening. Whereas if you're running away from the friend, that distance is becoming greater because you're running away from your friend. So that'll make sense that because it's symmetric too, it'll be the same number and it'll be opposite signs. So So that's the problem in one way. And I'm going to go ahead and solve it a different way. And this, I think, would make a little more sense if you've had some experience with vectors in physics. So what I'm going to do is I'm going to go ahead and reintroduce the problem. I'm going to go ahead and draw a X and Y coordinate system here. And I'm going to go ahead and draw the track. And you can think of the motion, around the circle as a vector. And also we can kind of consider the friend standing at the origin. So the friend's at the origin. So we're going to want to make a vector that relates the position of the runner. Relate that with the origin, or the friend, basically. So we gotta parametricize the position around the circle. And if you might already know this, but I'm gonna go ahead and just write that the position vector P is equal to, it's gonna be 200 meters plus the x component of the vector, which is going to be cosine. And I'm going to use a physics term omega, meaning the angular velocity times time, t. This is our x component of the position vector. The y component of the position, oh, and I'm sorry, it's r cosine t because there's a radius r. The y component of this position vector is r sine omega t. Okay, so we got this here. And now that we have this, we can do a few things. We can go ahead and let's go ahead and find the distance. The distance of this vector. So the distance d, it's the same thing as the magnitude of the position vector. And that's going to be equal to the sum of the squares of each component. So we're going to get 200 plus r cosine omega t squared. Oop, let me put another set of parentheses there. No, we already got the parentheses. Never mind. Plus r sine omega t squared. I didn't quite define what omega is. So omega right here is the angular velocity. The angular velocity is, there's an equation for it, which is velocity, the linear velocity is equal to the radius times the angular velocity. So omega is equal to v over r. So we could rewrite that as v over r if we wanted to. And I'm going to go ahead and rewrite this here. I'm going to do some algebra, and I'm going to expand the stuff inside the radical. So that's going to be 200 squared plus 2 times 200 times r cosine. I'm just going to go ahead and just rewrite omega as vt over r plus r cosine. So we're gonna go ahead and square this term, r cosine omega t, but then we're gonna add by r squared sine squared omega t. And I'll go ahead and show the steps. But we're gonna have r squared cosine squared vt over r plus r squared sine squared. Oh, I hope you can see this on the board. Vt over r. Really cool thing about this, we can factor out an r. Cosine squared plus sine squared is 1. So I'm going to rewrite this as 200 squared plus 2 times 200 times r cosine vt over r plus r squared. So we got another expression. It looks a little different from the previous one, but it's actually a bit related. It's a little geometrically, it's still a bit related. I am going to go ahead and there's a little bit of a trick you can do here because I got to take a derivative, but I don't want to deal with that square root. So I'm just going to square both sides. And we're just going to rewrite this as d squared is equal to 200 squared and everything on the inside there. Yeah, so that we don't have to deal with the radical. And now I'm just going to go ahead and take a derivative with respect to time. We're going to get 2 times d times dd dt is equal to, all this is constant, all this is constant. The only thing that's not constant is this stuff in here. So that's going to be equal to 2 times 200 times r. Derivative of cosine is negative sine vt over r, and then chain rule we multiply by v over r, and a couple r's cancel here, and I'm going to go ahead and divide both sides by 2d. So dd dt is equal to 2 times 200. Well, I'm going to put the negative out here. Sine vt over r times v divided by 2d. d is 200. So this is going to cancel with this here. The 2's are going to cancel. So this is the same thing as negative v sine vt over r. And now we're left with a little bit of a conundrum because what is t? What is time? How do we know what time it is when the runner arrives at that point? And that is a really good question because it's not something that you can easily solve like this. But we can go ahead and reuse our original equation over here. I'm going to use green. I'm going to reuse this equation here and just solve for cosine. So I'm going to put this on hold. So this is going to be number 1. So d squared. This is before we take the derivative. And plus r squared. So d squared. D is 200, so I'm just going to rewrite this as 200 squared. This is going to cancel with this here. And I'm just going to go ahead and rewrite this here as negative 2 times 200 times r cosine vt over r is equal to r squared. Cancel an r, why not? And we're going to go ahead and divide both sides by 2 times 200. So we're going to get cosine vt over r is equal to r divided by negative 400. R is the radius is 100, so we're just going to have 100 over 400, which is equal to negative 1/4. And I guess we could probably use a little bit of a trick because what we really want to know, we don't necessarily need to know what the time is. We can just find out what the cosine is, and once we know what this is, we'll know what the sine is. So we don't need to like specifically know the exact time. And the way we can find that out is, what if we draw a triangle, and let's call this angle vt over r. We know that the cosine of vt over r is 1/4. The negative doesn't matter because in the triangle it's just going to be all positive lengths. So if you remember SOHCAHTOA, the cosine is equal to the adjacent over the hypotenuse. So that means that the adjacent is 1, the hypotenuse is 4. So we can find the opposite value by using 4 squared is equal to 1 squared plus hypotenuse, or the opposite squared. So 4 times 4 is 16 minus 1 is 15. Square root of that is the square root of 15. So that means that the sine of Vt over r is equal to the opposite over hypotenuse, which is square root of 15 over 4. And now we can go ahead and plug that in. We're going to go ahead and plug in number 2 to number 1 here. And I'm going to use blue. So dd dt is equal to negative v sine of Vt over r. And I'm just going to go ahead and plug in for that square root of 15 over 4. And v is 7, so I'm just going to go ahead and do negative 7 times square root of 15 over 4. And to be fair, it could be plus or minus 7 times square root of 15 over 4. And that's because if you're looking at the original equation here, or the original drawing here, for the cosine to be Vt over r, it could be this point or this point, like we previously mentioned. I'll draw it in blue. This point or this point. So it can be positive or negative if you're using the reference angle. So I'm just gonna go ahead and write that in. It could be plus or minus because it could be second or third quadrant. So hey, we found an exact answer. We can just say that the rate of change is equal to plus or minus 7 times square root of 15 over 4. But usually if it's a physics problem, you probably want to give like significant digits, because in reality you don't really have 0.582986 infinite infinite decimals after a number when you're measuring a distance, because you have to think about your significant figures and all that. So square root of 15 times 7 divided by 4, and that's going to be equal to approximately, because now we're rounding to the nearest, plus or minus 6.78 meters per second, which is the same answer that we found in the previous way that we solved it over here. 6.78. And that's it. I hope you guys enjoyed this. Let me know what you guys think. If you're watching this on the YouTube, let me know in the comments. And hit the subscribe button if you'd like to watch more of this. And I'll see you next time. Have a good night.